we'll go ahead and just continue to move forward from here. But all that being said, we've just defined our inverse function. We found that stuff about it. So now we're going to use our knowledge of the natural log along with this e function to use them in equations, to use them for graphing, to kind of study a little bit of limits, and eventually to do derivatives and integrals. Okay, so let's start out first with, let's see, let's do a couple of examples. Okay. So let's say that I give you the equation, right? The natural log of x, and I want this to be equal to 246. Wow. Okay, we'll just do something basic. Okay. Let's find what x value that the natural log is going to be 246. Right? Now, one option you can do is you can, work with that integral definition, right, of our natural log, try to maybe see if you can make something easier out of that. But we're probably not going to have any luck. So what we do is we need to say, okay, if I'm going to get this x by itself, I need to do something with this natural log, right? But with our new kind of defining systems here, our inverse, right, it allows us to use these relationships that I have to be able to cancel each other essentially, right? Because that's what the inverse does. If I have a function, right, x, and I apply f inverse to it, that cancels those two out and leaves x's on the inside, right? Okay, so let's see. We're going to apply then our exponential function to the natural log here, right? And the way we're going to do that is we're going to use, right? So essentially, I need to put this natural log inside e somehow. I need to put both inside e. And the way we're going to do that, right, is I need e to the x power, right? We have here that add the exponential to the natural log of x is equal to x, which is the same thing in our case down here as saying that e, right? So e to the natural log of x is equal to x, right? If the exponential of x is the same thing as e to the x, then I just simply plug natural log into this function and they cancel each other out. So this is going to be a useful tool for us. So how I use it here is I'm just going to pick this. I'm going to make e the base of both, right? So as long as I do the same thing to both sides, it's still true, right? Because obviously if the natural log of x is equal to 246, then e to the natural log of x is equal to e to the 246, right? But now we know that the natural log and the e here are going to cancel out, which just leaves us with x. And then we're left with this number here, which is e to the 246 instead of our answer. Okay, so nothing too crazy and probably stuff that you should be familiar with. There's a little bit more defining, kind of building up that's going into this, but essentially we're just solving water equations using exponentials and also we'll be kind of backwards. But so for now, I'll do another one real fast here. Let's do, and we'll have e to the 4 minus x squared, and we'll let this be equal to 1. Okay, so we'll call this example A and we'll call it B. Okay. So now instead of starting with the natural log, I'm starting with e to some power, right? So again, we should be in a similar mindset, right? That I need to get that power down, right? I want to get rid of that, move the e away, do something with the e, just as I did with this natural log, so that I can get that power down and kind of work with it. Okay. So in this case, I just took e, everything to base e, and that canceled out and gave me the x I need. What should I do to both sides here to cancel out this e? What do we do? Yeah, Absolutely. We're going to take the natural log of both sides. So I'm going to take the natural log of this left side, and we're going to take the natural log of this right side. Okay. So on the left side, you can either work it out kind of similar to what we showed here when we brought down the x, and then it'll cancel out and become 1. But also, we just know for a fact that the natural log of each of the x is going to be x, right? So this left side is just going to become 4 minus x squared, and the right side is going to become, what's the natural log of 1? 0. Good. Good. Nice and easy. Okay. From here, how do I solve this? Yeah, it's just a quadratic equation, right? You should be familiar with this in an algebra setting. So you can either do like quadratic formula, but also there's no x term, so you could just, so I'll take this out here maybe. So we have x squared equals 4, right? So then we get x is going to be, right? So those will be the two solutions, right? But in order to get to that point, I first had to cancel out the e, or in this case, I had to cancel out the natural log, and you just use the inverses of each other. Okay. So again, we're really hammering in this idea of inverse, how these are related, and how you should see both if you're working with them and how they are interconnected. Okay. Cool. Let's see. So that'll be great. Again, here's the basic graph of E, right? And from here, we can also gather a little bit of information as we're going from the left into the right. So I'm going to write down a couple of limits here. First one is that the limit as x approaches e to the x power is, what do we think? Right, looking at this graph, right, I'm saying I want to take my x on the red graph and I want to make it go all the way to the right. Right? So if I take my x and I go all the way this direction, right, what's happening to the y? What is it? Yeah, it's also good. It just keeps going up, right? It's going to keep getting bigger and bigger, right? So the limit as I go all the way to the right of my graph is going to be infinity. That should be a general idea that if I have e, and I put taking it to infinity, it's going to grow huge. Okay. What if I take it the other direction? What does it look like? What does it look like it's happening? Yeah, it's going to approach 0, right? And it's approaching 0 because, right, what's happening, right, as opposed to this case, is I'm plugging in not positive powers and it just keeps getting bigger, but I'm plugging in negative powers, right? And anytime I have, for example, if I have just add, well, actually, that's fine. For the negative power, what can I do with that x? Yeah, put it in the denominator, right? So we get 1 over x to the n. And so that's the same thing that happens here. So what's happening is if I'm putting in negative powers, and so this essentially just turns into 1 over e to, and I'll go ahead and write this. This isn't technically formal, but this is kind of what we're looking at, right? We already established that e as it goes towards infinity is infinity, right? So what's happening is we have 1 over infinity. Well, it's 0, right? It's going nowhere. Okay. So these are good to look at. I think the book does. I'll do a quick example of that. Get into this a little more because I find that it's good to kind of spend time on some of this stuff because a lot of times people will know the derivatives of the integrals, but then they can't, but they don't really have a connection because they're not understanding the graph of how e to the x works. And, they might remember this, but as soon as you do like e to the 2x instead or something, they're like, oh wait, now what do I do? But it's the same thing. Okay, so let's take just a quick example. Move on to some laws and do some derivatives and integrals. So I'm going to take the limit as x approaching infinity of e to the negative x squared power. have some basic ideas here, right, which could translate, but in these cases, we still need to be thinking, really thinking about what's happening in this problem, right? So I want to find the limit of this guy, e to the negative x squared, and I want it to approach infinity. So what's maybe a good first step here to work with this, right? Can I just plug in infinity? Would that be a good idea, or should I try to change it? What should I do? Good suggestion. Good, right? Because it's still a negative power, right? Same thing here, right? It's negative x squared, right? Don't need to think about that as anything different. So I'm going to get the limit as x approaches infinity of 1 over e to the x squared, right? Good. Okay. Now, whenever we're dealing with limits, if you remember, one of the limit laws we have is that I can take my limit and I can do each part individually, right? Which we kind of use here, but specifically when you're doing the problems, you might want to remember that. Okay, so we're looking at the top. What's the limit as x approaches infinity of 1? Just 1. It's just whatever it is, right? It's just, it doesn't change. What's the limit as x approaches infinity of e to the x squared power? What do we think? So it's still going to be infinity, right? And I mean, we can use this, you know, for as a starting point, right? I mean, if e to the x itself goes to infinity, right? X squared is bigger than x, right? So if I put infinity into x squared, it should grow exponentially faster. Okay, so we're going to get 1 over, we said this approaches infinity, essentially. Again, this isn't the most formal, but you get the picture. So what is this approaching ultimately? What number? 0. Yeah, it's going to approach 0, right? If I have a number like 1, 2, 3, 4, 5, whatever it is, over infinity, right? It's going to be nothing essentially at the end, right? That number is not going to matter because this is going to be so big that the denominator is going to be so big that whatever the numerator is doing, it doesn't matter. Okay, so this ends up being 0. Okay, so there's a few limit problems in that section. I thought I wanted to address the idea real quick. Go there. You can also, if you want to, another way you can do this as well, I'll mention, is that, and this is something that kind of ties back to talking about continuous functions. I mentioned something about continuity yesterday, but if I have a continuous function, what I can do is I can take this limit and kind of bring it further in, right? So I have e to the negative x squared, right? E is a continuous function, e to the x at least. So what I can do is I can leave the e here, like the limit can just kind of face through that, and I can rewrite this as e, and then take the limit as x approaches infinity of negative x squared, right? Which this, what is this? What is negative x squared going to approach as we approach infinity? What's it going to approach? Negative infinity, right? You put infinity in there, and ignoring the negative, it's just an infinity square, which is still an infinity, right? So it keeps getting bigger, but then there's a negative sign plopped on the front of it, which makes a negative infinity. So in term, we're getting like e to the minus infinity per se, right? Which then, again, I can kind of bring it down, and kind of our logic up here, it's going to turn into 0. But either way is valid. There's a lot of ways to think about this. We do need to be really thinking about limits again. I would encourage you to read in the book. There's sections that talk about kind of doing curve sketching and stuff again, which won't be as much our main focus because that's more of a really cover on focus topic. But you need to be remembering that, you know, for the future, because it's going to be helpful for you to understand what a curve looks like in some cases. And knowing these, how to do limits and what the graphs look like is going to be very good. Okay. Questions on any of this? Nope. Okay, cool. Let's move forward. more fun calculus stuff here in a sec. We do need to establish, again, though, just as the natural log has 3 rules, right? Exponentials also have 3 rules, right? Now, the first rule, or we have laws essentially with our exponentials, right? So this first law, right, deals with what if I have 2 things adding in the exponent? So I have e to the x plus y. Okay. So what can I do with that x plus y? How can I rewrite this? Is there a way I can rewrite this at all? Any ideas? Yeah, right. There's absolutely. So what we can do, right, is I can actually rewrite this as e to the x power times e to the y power, right? So I can take that x plus y and I can just separate it to each base. Okay. So I can essentially, instead of having to add up this one big thing, I can do each individual piece and look at it that way. And sometimes it's easier to break it down, or maybe it's easier, like if I have, as an example, e squared times e cubed. Well, I don't need to do e squared and e cubed. I can do e to the, go backwards, 2 plus 3, which is e to the 5th power, right? No need to have e squared and e cubed. Just do it together. Okay. Now we'll do a quick little proof of this rule here, just to show. And the way we're going to do this is we're going to use our knowledge of the natural log, right? So I'm going to take e to the x plus y, and I'm going to take the natural log of e to the x plus y. When I take the natural log of e to the x plus y, what do I get? You get x plus y, right? It's just the power, right? You can either use the power rule, bring it down, know if that's 1, or just remember that those cancel each other out. So it's just x plus y. Okay. But we know that if so they're adding up individually together, right? So we know that x, right, I can write, now, obviously I'm not going to expect you to just think of these things as like, oh, of course, it's intuitive, I see it, but just, you'll see like the comparison from here to here. I can rewrite x as the natural log of e to the x power, right? Because these cancel each other, so it's just x. It's a funny way to write x, but it's still x, right? And I can do the same for y, which is going to be plus the natural log of e to the y power. Okay. I have 2 logs adding up to each other. So what law do we have? What can I do with the things inside the natural logs? Right? These are adding. I can bring this into one natural log by doing what? Multiplying. Yeah. I have it up here actually from yesterday. We have the natural log of x plus the natural log of y is the natural log of x times y. Absolutely. I can just take them and multiply them together, right? Kind of combine them back into one log. But what we have now is that I have that this n is equal to this n. And most importantly, they both have a natural log on it, so that this thing is equal to this. So we have it. Okay, so that's very useful. That helps us a lot. And I'm sure that will come back later, but there you go. We have a couple extra laws that will also come in for those. So now if I have e to the x minus y, how can I rewrite this? Oh, wait.
EX divided by EY.
Good. Yeah, so you actually can just take e to the x divided by e to the y. And this also goes backwards, of course. And this just uses, you could just use this guy as a start, but then just remember if I have a negative exponent, it goes in the denominator, so we get this. Okay, and our last law here, you're going to have E, let's see. So if I have E to the R times X, so just some number times X essentially, this is equivalent to saying E to the X, and then raise that to the R power. Okay, so, and also it could be true the other way if I wanted, for some reason, wanted E to the R, and then raise that to the X power, right? So what we're saying is, if I have E to a power, and then I raise that to another power, I can just multiply those two powers together, right? Or go backwards for that. And that works another way, okay? But these three rules are going to be fundamental for us as we go through. I mean, it's they have very similar pairs to those the natural log ones we already defined. So, questions on any of that at the moment? Yes, no, maybe so. Okay, fantastic. Let's finally talk about the derivative of this thing. So I guess that means we're done with this game. Fantastic. 6 more points left. Okay. And we'll have a break in between, of course, so don't worry, I won't talk. So we need to figure out, right, if we're studying this function, right, we have all these walls to break it up. We have an idea of the graph, maybe the shape where it goes. We have our limits, right, but we want to know how each of the x changes over time, right? How the slope's changing, what we can do with that. That's going to help us to further study this. Okay, so we needed to figure out, well, what is the derivative of e to the x going to be? So I don't want to just give it to you, so let's kind of work it. Okay. We know what the derivative of the natural log is, right? Because we just found that yesterday, and that's its inverse function, right? So remember, if I know y equals e to the x, this is the same thing, right? And maybe I'll put in parentheses here that x function is the same thing. This is nicer in terms of like, oh, I see the clear number I'm using in this case. This is the same thing as saying that x is equal to the natural log of y, right? Which again, that's from our definition, or you can just apply the natural log to both sides of this equation, and we'll get there. Okay. Now my ultimate goal is to find the derivative of 1, which is e to the x. Okay. So I want to take the derivative of this thing, right? Because I know how to take the derivative of each one. So let's do that. So I'm going to take, so again, I'll write x, y, and I'll just take the derivative of both sides. So what is the derivative of the left side going to be? Just 1, right? It's just x, right? So it's just going to be the number 1. Okay? What's the derivative of the natural log of y? One over y. 1 over y. Good. And then multiply this by dy. So we have 1 equals 1 over y times dy over dx. So what does that tell us about dy over dx? What can I do with that y? So dy over dx is equal to y. And what's y? Yes. How about that? The derivative of e to the x is e to the x. There you go. Easiest derivative you ever have to do. The derivative of e to the x is itself. So it's very fancy, very helpful. Pretty simple. Not anything too crazy with that. Of course, we're going to deal with some chain rule stuff here. It's going to pop out, but in general, right? Anytime I'm dealing with the derivative of the exponential function, it's just itself, maybe with some things added on. So let's do a couple of examples here. Okay. So let's do, so I have e to the x cubed. And I want to take the derivative of this thing. Okay? So if I'm taking the derivative of e to the x cubed, right? So what rule do we need to use here? To do this? Chain rule, right? Because we have some function that's other than x here, right? So the derivative of e to the x is e to the x. So I'm just going to write down e to the x cubed again. It's just simple as that. But then I just need to multiply by the derivative of the function, which is what? What's the derivative of x cubed? What is it? 3x squared. Fantastic. And that's it. Yeah, that's so bad. Let's do it. Sure. All right. We'll do the actual numbers. Okay, and we're going to take the derivative of this function. Okay. What rule or we use product rule because I have two different functions. I have e to the x plus 2 and I have the natural log of x. Okay, so we'll start off first. Let's start off. We'll start this time with the derivative. We'll leave the first one, right? E to the x plus 2. Then we'll do the derivative of the natural log of x, which is 1. I think I heard it. Derivative of natural log of x is 1 over x. So we have e to the x plus 2 times 1 over x. Okay. Plus, now let's. So now we want to leave natural log of x, and we want to say what's the derivative of e to the x plus 2. So how do I start it? How do I start the derivative of e to the x plus 2? E to the x plus 2. Every time, just write down exactly what's there, right? Okay. And then we multiply by 1. Yeah, because the derivative is just 1. So use it. Okay. Again, we can do more complicated examples of power. The book covers that plenty. I don't need to. We don't need to just sit here the whole time and keep talking about, oh, what if I put this in the E, or what if I put this in the E? We just do that. We'll be good for now. Okay. Any questions on that? Yeah.
Would you not use the chain rule in the second? Use ex plus 2?
So we did, right? But the chain rule in this case, right? You get e to the x plus 2, and then you multiply by 1.
Oh,
right? Because what's the derivative of x plus 2? It's just 1, right? So you are using chain rule, but really it doesn't matter. It's just multiply by 1. Now, if I had like x squared plus 2 in there, right, then you'd have to have 2x, and so then you would have to work in those cases. Good example, maybe, to make sure we catch people. If there's a plus 2, what they do. Oh, it's a 2, and down there. Okay. Another example here. Are we good on this? Is this fine? This really isn't too bad. It's no wonder the book spends a while doing the first stuff. This doesn't take very long to explain. So cool. Yeah. Okay. Well, I guess that we'll leave that there. That's good. We're done with our derivatives for that function. Again, depending on how much we left at the end, I can always like do some more examples. Things, but I want to make sure we cover the topic at hand. So that was nice and easy. Okay, now comes the hardest part. We just need to figure out what the integral is of E is. What's it going to be? What could it possibly be? Just easy. Yeah. Let's see. Let's see in that case. It's just e to the x, right? If the derivative of e to the x is e to the x, then the integral of e to the x is e to the x, right? Because you can just think about it going in the opposite direction. So the reason why we like the, I'm sure you've seen in other classes like having, and we'll get to that in 6.4, having other bases, right? The reason we like to work with e and natural log is just because they're so nice. They happen to be so nice when taking derivatives and everything, and it comes together really well, and it helps us evolve things. Few examples, especially like find derivatives and integrals and other kinds of things. Okay, there's that. So we can a little bit if you want. That's really all it is. So we'll do doubles. We'll do double example on this. Okay, so example number 4. Let's see. Let's do the integral of do this integral, okay? Because obviously all of our integrals like can't just be e to the x. Okay, so we have the integral of cosine x times e to the sine x dx. So I need to integrate this, right? I have an e involved, so it would probably be ideal to get it back to this form in some way, right? So what ideas do we have for this? What should we try? Substitution, what would you be? So I wouldn't necessarily do cosine, right? Because so let's think ahead on that, right? So if I were to suppose it were cosine, right? What would du be in that case? It would be negative sine, right? Sine x dx, right? So what would happen is, the sign that's here is inside this section, right? It's e to the sine x power. And so I wouldn't be able to replace that with this dx, right? Because it's only if it's multiplied with the dx. But also, even if I try to just get the dx by itself, fix it, there's no way it's going to be able to cancel nicely in any way. So we don't want to pick cosine x. What should we pick then? Sine. We'll do the one that's inside the function, right? That's a general rule when we're doing u substitution, right? The easiest u sub to do is try to do the part, plug into the part that's causing you the most issue, right? In this case, it's this e to the power thing. I want to make that the u, right? Or inside a square root, you might make the thing inside the square root u, essentially. That's not always the case, but it might be a good idea to try pretty often. So we get u as sine x, and we get du as cosine x dx. Okay, do we have that here? Do we have cosine x dx? We do. Cosine x times dx, right? It's not in the e now, it's just by itself. So we have u up here, and we have, this is du, right? So this integral is going to become the integral of what? E to the u du, which is what? E to the u plus c. What was u again? And we're done. That's all. Nice and easy. E to the sine x plus c. All right. Okay. Does that make sense? We good there? Okay. I'm going to do one more example. this, and then we'll take a break. So. Okay. So this last example, let's see, what function do I want? Let's take the integral from 0 to square root of e times b to the x squared dx. Okay, so let's get some definite integrals going in here. We don't just want to work with indefinite ones. We need some bounds, you know, to make sure we got know what's going on, got our skills still, right? So, okay, so I want to solve this. That's my first step. Use them. Good. What's you gonna be? You. All right. So again, there's a few ways to do this, and I talked about kind of how to go about this yesterday. What I'll again keep consistent. I'm gonna kind of show you what my methodology is for this. So inside the integral we have x. We have dx, right? So x dx is that thing that's outside of the e to the x squared. Right now I have 2x dx, and so what I don't want there is that 2. So I'm going to take both sides, I'm going to divide it by 2, which will leave us with du over 2 equals x times dx, which is what I have now. Okay? So that's going to make our problem. So let's rewrite everything, right? What's that going to change everything into now once I plug in that u? Right. Let's at least focus on like this part. What's the inside going to turn into? Right. So I have. Yeah, so we put the 1/2 on the outside, then we have e to the u. Okay. Now, again, there's a lot of options when it comes to u substitution. So, and what I think I'm going to do is I'm going to go ahead and change my balance in terms of u. Sometimes you might learn in your classes to say, oh, let me, I'm going to do the integral and then find what it is and plug x back in and then do my balance afterwards. Okay. But if you decide to take your integral and switch it in terms of u, especially if it's a definite integral, then I can always take those bounds and I can transform them as well. I can say, oh, well, it's u now, so let me just bring them into the u world. I don't have to worry about that with my indefinite integral because it's, I mean, I want it in terms of x anyway. I want a definite, like, this is the antiderivative. But here I'm just looking for a value here, so it doesn't matter, right? So u is x squared, right? So I'm wanting to change everything from x into u, right? So what am I going to get when I take the lower bound, 0, plug it into x squared? What do I get? Still 0. And if I take the square root of the natural log of 2. Okay. So now our bounds are going to be 0, still 0, nice. But now instead of the square root of the natural log of 2, I'm just going to get the natural log of 2. Okay? Does that make sense? Is that clear there? Again, you can, if you have any questions, you can always reach out to me and talk through it. But want to try to keep consistent with these methods for the most part, so we don't get too lost in all the craziness of, oh, well, you have 6 different options. So let's do it. Okay. So with that all being said, let me make some more space here. The integral v to the u. C to the u, yep. And then we want to evaluate from 0 to the natural log of 2. So we have So I take natural log of 2 and plug it into u. So I get 1/2 e to the natural log of 2 minus 1/2 to the 0. Okay. What's e to the 0 power? It's 1, right? Now, for any of those who might have been unsure, just remember, so natural log and e are, inverse functions, and we remember the natural log of 1 is 0, which means that e to the 0 is equal to 1, right? They're kind of the x and the y get flipped in that case. So e to the 0 gives you 1, and the natural log of 1 gives you 0. Okay, so this is going to give me 1/2. 1. What is e to the natural log of 2? I'll heard someone say that. E to the natural log of 2. E and natural log are what? How are they compared to each other? They cancel each other, right? They just cancel each other out. So this 2 just comes out. So I get 1/2 times 2. So e to the natural log, remember, e to the natural log of x, and the natural log of e to the x is x as well. Okay, keep that in mind. So if you see this, that just becomes whatever x is. In this case, it's 2. So I get 1/2 times 2 minus 1/2 times 1. What's 1/2 times 2? 1. And what's 1/2 times 1? 1/2. What's my final answer? Any questions here? Let me know. That's it for this section. Again, if we have time at the end, I can cover maybe something more difficult or like something more interesting, but that's good for that section. So we're done with that. Time is it? Oh, we're doing pretty good. Once you guys have a 10-minute break again, then we'll put into the next section, which might take a little bit longer. If you have questions.